In this part of the lecture, we'll be taking a look at how NMRBox would be useful towards analyzing some NMR data. The first thing you need to do is to go sign in. I hope you all have created your respective accounts. Once you click sign in, put in your username and password to sign in. The moment you sign in, you will have a page like this where you'll be shown different servers that are available with NMRBox, and you will be able to connect to the one that is least utilized. So for instance, in this case, the hydrogen one is least utilized, so we can end up using it. Even before going ahead on how this could be used, you also need to download a client. In this case, I use the VNC Viewer client, which is available for various platforms, including Windows, Mac, and Linux, which are most common. So I suggest you to take a look at it. And once having downloaded this VNC Viewer, if you install it, you're going to have a program that looks like this. If you have a previous login, then you will be able to see something up as shown here. But now I'll try to show how this could end up helping you in logging in. If you typically click connect, it would open a file via the VNC viewer. If you click OK, it'll end up helping you to establish a connection. And in cases that this is a little difficult to do or it takes forever, you may stop it and look at the downloaded file. Then you would find which login is being used. In this case, hydrogen.nmrbox.org. So go back to the VNC viewer, hydrogen.nmrbox.org, and hit enter. And we'll try to connect. It'll ask whether you would like to identify this as a known source. You just go ahead and click continue. You would realize that you're connecting to hydrogen.nmrbox.org. Say continue. The moment you say continue, it's going to ask for username, password, just the same one that we had used earlier in the account. So the moment you log in, you're going to see where the VNC viewer takes you to the file system. Wait for a few moments until the graphics start to come up as sharp as it could. That means that it is fully rendered. It takes a little bit of time based on your internet speed to have this looking as crisp as it could be. And you will be able to navigate the folders just the way you would end up doing. What you're using here is called the virtual box. Basically, a computer is running elsewhere. As you see, hydrogen server is in Korea. We are accessing that, and we'll end up using the data that is present here and the software that are pre-installed that will make our life easier. So in order to download the data that I have posted, open a web browser and go to my official web page, which is https://bionmr.wordpress.com. You go to the course code, you will be able to find the desired file located in Google Drive. You do not have to log in to do any of this, so just click G Drive. It takes you to a folder where you are able to see the file that I have uploaded for you. So click this and you can say download. Once the download is complete, you would be able to find the document in the downloads folder. You may close the browser. It's not required any further. Home, downloads, you'd find this given folder. I'd recommend you to create a folder on the desktop by name NMR data by basically right-clicking here and say create folder. Once you're able to do this, then you will be able to create a folder with the name NMR data. Move the zip file into this folder and extract the components of this given file. Having done this, you may close all these folders. Then you would have to end up opening a terminal, as you see here at the bottom with a $sign and a black box and a cursor waiting for you to type a command. You click the terminal box, you end up seeing a command line that opens up of this sort. The command prompt here, you can type the software you would like to open, in this case topspin. If you hit enter, Sometimes it may ask a question of this sort, and if you're opening for the very first time in your NMRBox login, it might ask you for terms and conditions where it says you're going to open only one instance of it at a given time and also close it once your work is over. If you do end up getting a question like upgrade, you can just say run any given topspin. It doesn't matter to use 4.09 or 4.06. Both work the same way for us. What you're able to see here now is that the topspin software is now open. Once you have maximized the screen, go to the data window and add the file that you have just put in. So the way to do it is to right click in that window and go to add new data directory as you see here and click add new data directory, and it's going to ask the name of the directory which you'll be able to browse from these three dots that are present, and then say desktop is where you have saved, and you can click NMR data, you can say OK, then you can say CHM627 NMR data for instance and say OK. Then you have the folder that ends up coming. Click here, you will be able to see the data set that you want to take a closer look at. This is the data that has been acquired for the camphor molecule in DMS or solvent. Once you double click each one of the numbers, these are the data that has been collected for this given molecule. Basically, you can think of 1, 2, 3 as the experiment numbers. ZG stands for the proton one-dimensional NMR experiment, and what you are able to see is the data that has been collected for this given molecule. You would be able to use your mouse left click and drag in order to zoom in to certain portions that you would like to take a closer look at. The scroll helps you change the intensity of the resonances you're looking for as well. Since the data was acquired with the spectrometer legs down, you will see some artifacts, but that's not going to hamper our data analysis right now. What you're seeing here is a solvent residual proton peak. And if you go here, you would be able to use start distance measurement toolbox. Basically, it will help you measure scalar couplings, the difference between the peak maxima of this multiplet, and you're able to read out a value, something like 1.83 Hertz. And you can also use other tools here. For instance, if you go to analyze, you'll be able to say pick peaks. You can manually pick or auto pick. Just for instance, let's say you auto pick, you're able to see the peak maxima has been nicely picked up by the software. And if you go to the peaks tab on the top corner, you will be able to see all the peaks that have been picked up. So basically, these are the resonances that you're looking for. You could also add additional tabs into this, where if you right click on the purple ribbon there, you would be able to add the half width as well, just for an instance. And then the half width starts to come up as the final column that is present here. You can also save the peak list by right clicking and say export, and you should be able to export it in different formats, including a very simple text format. Let's go back to the data folder, and then you can browse across the different experiments that have been provided to you. Experiment 2 is a simple carbon one-dimensional NMR experiment, which we have discussed in detail in class, and experiment 3, 4 and 5 are the DEPT 45, DEPT 90 and DEPT 135 spectra. In order to overlay these spectra one on top of each other, you can go to this menu up top which says multiple display. You can also type the command .md, the command prompt that you see at the bottom here. Alternatively, if you're a person who likes to use the GUI, then you can click the multiple display GUI here. Once you have clicked it, all that you have to end up doing in order to add more data sets into it is to click, drag and drop the DEPT 45. The moment you drop it, you're able to see that in addition to the dataset 2, which is the carbon 1D, dataset 3 is also added, which is your DEPT 45 experiment. And the colors are different so as to help you distinguish what dataset has been added on top of each other. Let's add more data sets into this. Let's also add the DEPT 90, which comes up in green color, and the DEPT 135, which comes up in purple color. Just to exemplify the point, you would be able to zoom in further into the peaks that you want, and then you'll be able to move the spectrum such that you can maximize and take a look at how these different experiments have actually behaved. In this case, the sensitivity of the carbon 1D experiment is high, so you may reduce it largely because it was occurred for a much longer time. Now you will be able to zoom in order to see the characteristics much better. You can use the multiply by 2 and divide by 2 functions in order to increase the intensity of all the spectra on the top corner. On the other hand, if you only have to change a given spectrum that is in blue color, you select the spectrum in this window and then go click star to S and slash to S for increasing by 2 times and decreasing by 2 times. In this spectrum, this resonance has a positive signal in the DEPT 45, no signal in DEPT 90 and negative signal in DEPT 135. That clearly indicates this is a CH2 system we are looking for. On the other hand, this resonance, which is a little more upfield to the previous resonance that we saw, is positive irrespective of any of the flip angles that are used in the DEPT experiment, indicating this is a CH spin. I leave it to you guys to interrogate how the other resonances behave for Camphor by slowly zooming in and taking a closer look at how different DEPT and carbon experiments help you do spectral editing. Having done this, you can return by clicking the return button up there. There are a few more data sets that have been provided for you. The data set 6 that you're looking at is the Cosy experiment. If you double click the number 1 data set, you will be able to see the Cosy spectrum. Cosy is an experiment that helps you correlate protons that are scalarly coupled with one another. You would also be able to overlay one-dimensional proton NMR experiments. If I type .md, it will help me throw the proton 1D experiment, which you would be now familiar with, as shown here. Just for an instance, I would like to show that. So what you're able to see is that there is a cross peak that exists between this set of resonances along with these doublets that are present. So therefore, this indicates, and there is also a transpose peak that is present, indicative of the cross peak pattern that is observed in a Cosy experiment. I leave it to you guys to further examine what else is present. In experiment 7, you also have another data set, which is once again a Cosy experiment, but this is called Cosy 45, where once again you will be able to see cross peaks between spins that are scalarly coupled. In this Cosy 45 experiment, it has been smartly done such that when you change the flip angle from 90 degrees to 45 degrees, the diagonal and cross peak intensities are carefully matched in order to get the spectrum and analyze this data carefully. So as we go forward, the data set 8 is that of the two-dimensional nuclear Overhauser effect spectroscopy experiment, which is a NOESY experiment. In this NOESY experiment, what you're going to end up seeing is protons that are very close to each other in space. Will give you cross peaks with each other. And data set 9 is the two-dimensional heteronuclear single quantum coherence spectroscopy, which is HSQC, and you are able to nicely see the resonances that are present for Camphor. Here as well, you will be able to overlay spectra. Let's overlay the proton 1D and the carbon 1D spectra. And if you zoom in, for instance, to the methyl groups, what you're able to clearly see is that this given methyl group that gives a two-dimensional CH resonance indicates which carbon it ends up interacting with. Basically, that is at 0.76 ppm ends up interacting, or rather ends up having a carbon whose chemical shift is at close to 20 ppm. On the other hand, the resonance that is present here, which is at 0.8 ppm, gives you a cross peak which has a carbon resonance 10 ppm. So this helps you understand how two one-dimensional experiments, when correlated in a 2D fashion, helps you assign the proton and carbon spectrum easily. Experiment then that is present here is the HMBC experiment, which is a heteronuclear multiple bond correlation spectroscopy. Once you open the data set, it might say that the defined levels are outside the range, but do not worry. If you keep increasing the contour level, you'll be able to see the resonances that end up coming. Here once again, I suggest you guys to overlay the HSQC spectrum, which is experiment 9 on 10, and this will beautifully tell you how the HMBC and HSQC help you analyze the data. Not going to give you much of details here because this will form the part of your assignment. So just as an example, let's also throw the proton 1D experiment so as to make our life easier, and the carbon 1D experiment. So let's zoom in once again in the carbon methyl region. So these were the resonances that we were assigning using the HSQC. What you are able to understand is that the resonance at 0.8 ppm that correlates with a carbon shift at around 10 ppm ends up having other carbons that also get correlated. And what you are able to see from the carbon 1D spectrum is that these nicely correlate with the other carbons that are present, meaning that the proton's coherence ends up jumping not one carbon but multiple bonds in order to see other carbons and help you establish a correlation on who are its neighbors. Similar can be done for each of the resonance that is present here, and therefore you would be able to build up a network of resonances. I would ask you to be a little cautious interpreting the data. Only if you see a proton resonance that corresponds, then it's a HMBC peak. For instance, when you have the red resonance here, which comes from the HSQC, you're also able to see the two blue resonances that are present. This ends up coming although you don't have any protons that correlate with them. So that is the advantage of overlaying multiple spectra. Then you realize this is nothing but a single bond coherence that comes up as an artifact. And you will realize that this is an experiment where you do not decouple during acquisition, resulting in the doublet that is observable. We will see how to look at pulse programs in a moment. The 11th experiment is the two-dimensional J-resolved experiment, which gives you scalar coupling in the indirect dimension with proton chemical shift along the direct detect dimension. Let's take for an instance the doublet that's well resolved in the 1D in order to exemplify how this works. Just overlaying the proton 1D on top of this J-resolved experiment. Then I'm zooming in on the doublet resonance. Although a doublet doesn't require the J-resolved experiment, this just helps you understand the concepts much better. What you are able to see along the y-axis is that it comes up as J coupling, however it's still plotted in ppm. If you go here and then right click, then you'll get a menu called toggle units. If you click that, then the F1 comes up in hertz. And now if you are able to pick up the hertz for this resonance and the other resonance, difference between them would give you the scalar coupling that's present between these two moieties. These experiments are provided to you in order to understand even further how NMR works. In addition, please take a closer look at the assignment that is being provided to you, where you need to answer what parameters have been used in this experiment. It opens the ACPARS menu, which indicates all the parameters that have been used in this given experiment. Let's go one by one. The pulse program that you're using is ZG, and the acquisition mode that you're doing is digital quadrature detection. The total number of complex points TD is given by 32K points, where K stands for 1024. The number of dummy scans is set to 0, and the number of scans is just set to 1 in this case because it's a very concentrated sample. And in the width window, you're able to see the spectral width that's set to 5 ppm, and the spectral width in hertz as 3501.4 hertz. So therefore, if you divide 3501 by 5, you're able to realize it's 700 hertz per ppm, indicating this data is acquired in a 700 megahertz spectrometer field strength. You also have other parameters, is the total acquisition time, which is of about 4.68 seconds. Be very careful about the units that are used, and the resolution of the FID is given by the in hertz that you're able to see here, meaning that you'll be able to get even a 0.2 hertz resolution for the spectrum that is obtained. There are more parameters that are listed under this menu, but instead of going over one by one, it's much easier to interrogate with the terminal command here to ask for some parameters. For instance, if you want to type what is the D1, which is a recycle delay, it tells you it is 3 seconds, as you're able to see in this menu here. On the other hand, if you type what are the dummy scans, which is DS, you will be able to find what are the dummy scans that are present. Similarly would be the case where you have number of scans. If you type NS, you will be able to find what is the number of scans, and so on. So the commands that are required for you to find out these parameters will be given in your assignment. You need to go over each parameter that has been set for this experiment such that you make a table. If you want to take a look at the pulse program that has been implemented, you type the command called show pp, standing for show pulse program, and then you hit enter, which gives you the pulse program as indicated here. And what you are able to see here is that the pulse program starts with a D1 delay followed by a pulse that is applied for 7.75 microseconds with a phase that changes as 0 to 1 so on. We will read more into this as we go forward, followed by the data acquisition in form of the FID. In order to read the pulse program a little bit more in detail, either you can click the edit command here, or you can also type the command in the terminal mode here, which is edcpul. Once you type this command, a text file opens which has all the details of how the experiment is implemented. Basically, what you see here in this is a file which is the pulse program by itself. And all the details of this is very clearly given, where it starts by zeroing any data that's present in the file, waits for about 30 milliseconds, implements the D1 recycle delay followed by a pulse for a duration of P1 with a phase PH1. During the acquisition you have PH31. After you've done that, of course, go back to 2 and keep repeating this for the total number of scans that have been implemented. The last line just indicates to save the information and exit. And most importantly, the PH1, which is the phase of the pulse that is applied, is shown here. If you see, the receiver phase is set to PH31 and the phase of the pulse is set to PH1. And the phase cycling, which means the different phases that are applied to these pulses and the receiver, is shown in PH1 and PH31 at the bottom. Here, a 0 indicates an X phase pulse, so therefore 2 indicates a minus X phase pulse, Y indicates a Y phase pulse, and 3 indicates a minus Y phase pulse. So basically, PH1 is set to X minus X minus X X, Y minus Y minus Y Y. And if you scroll further within this pulse program, you would actually have more details that are given for the different variables that are used. For instance, PL1 stands for F1 channel power level for pulse default that is set. Since this is a single channel experiment where you are exciting proton and detecting it, by default the first channel is the F1 channel, which is proton. On the other hand, P1, which you ended up using for the pulse, is defined as F1 channel high power pulse. You have the ability to change the duration of this pulse so as to implement a desired flip angle. On top of it, the D1 delay, which comes before the P1 pulse, is the recycle delay or the relaxation delay that's set as 1 to 5 times T1. And the number of scans is 1 star n, indicating that there is not much of a need for phase cycling, but it would end up helping in some cases. So basically you can have any integer multiples of the number of scans in order to finally get your signal. Let me open the DEPT-90 experiment so as to understand how the pulse program looks. In this pulse program, you have 2 channels. One channel where you have the carbon, the other channel where you have the proton. And in this case, the F1 channel is set to carbon, as you are able to see the detection is done there, and the F2 channel corresponds to proton. And as we walk through the pulse program, what you are able to see is that following the D1 delay, you have the first 90 excitation that happens in the proton channel. Following the proton excitation, you have a tau delay that is set as D2 delay, followed by the 180 degree pulse, which is nothing but twice of 7.9 is 15.8 microseconds, the 180 degree pulse that's applied on the proton channel. While this 180 degree pulse is applied, you have a simultaneous 90 degree pulse that's applied on the carbon channel, which is of 15.4 microseconds at the highest peak power for the spectrometer, followed by the D2 delay, which is what you started with. If you might remember, the D2 delay is set to 1 over 2j in this case. So therefore, one of the exercise would be for you to calculate what was the j that was used in this example. As you go forward, this is the following tau delay, and then you have a 180 degree pulse on the carbon, which is a shaped pulse. We will not discuss more about this, but you are able to see the flip angle that is set in the proton as 7.9 microseconds, indicating it's equal to the first pulse. Therefore, you have a 90 degree pulse excitation followed by the D2 delay and acquisition with decoupling in the proton channel. So therefore, this will give you the DEPT-90 experiment. Just for the sake of it, we will also take a look at the DEPT-45 so that you see the last pulse that's applied on the proton is actually half the duration of the initial pulse. So for instance, this is the first 90 that's applied on the proton, and the last pulse that you see in the proton channel is half of 7.9, which is 3.95 microseconds. Apart from this, everything else remains same, including the D2 delay and the other pulses that are applied, so as to apply a DEPT 45 experiment. Once you have finished your job, you can always go to the button up top here and say log out by clicking this button down here. So once again, you have the menu that comes up from this top left button, and then you click this in order to log out. Then it'll ask you a bunch of questions, whether you want to log out, restart, shut down, and so on. Just click log out, and that will ensure that your session is done